Okay, so the next topic we're going to take up is alkylation of enolates. So we've already looked at it briefly in some of the previous discussions that we have had. So in principle, we know that a ketone, when you add a base, for example, when you add a strong base like LDA, it can pick this up and you generate the enolate. Okay, so this is something that we have looked at. Now, one important point here is that when we add a strong base like LDA, such as LDA or NaNH2, so LDA, NaNH2, and so on, there are quite butyl lithiums and so on. There are quite strong bases that one could use, and these actually make this an irreversible process. Okay, so this process that we're looking at, it becomes irreversible. That means that the enolate formation is something that does not go back to form the carbonyl compound. So if you adjust the reaction conditions carefully, if you, let's say you go to low temperatures and so on, this can have a very significant population in the solution, right? But now you can also do the same process by dealing with or by resorting or using bases which are not as strong. Okay, so for example, you can use amines and so on, right, which have a lone pair of electrons. So this can happen, but this is going to be some sort of a equilibrium. So therefore, when you use a weak base, this deprotonation occurs to some extent, and depending on the pK of the base, the pK of the conjugate acid of the base, if it's comparable or lower to this carbonyl compound, then you end up getting an equilibrium. So this is basically an incomplete enolate formation. Okay, so case number one is when you have a very strong base such as LDA, NaNH2, KNH2, butyl lithiums, and so on. And the case number two is when you have a weak base which can react with the carbonyl compound, but it doesn't produce the enolate completely. So these are important for us to understand, because later on in this lecture we will look at methods to control these kinds of enolate formation, especially when you have a couple of choices for enolate formation and you would like it to go along a particular path. Okay, so now let's quickly look at some examples of alkylation reactions. So the example that maybe we can start with is with this ester, 3 double bond O, OR, and you have a hydrogen here. And now let's say we use LDA, and now there's an abstraction of this hydrogen, and you end up forming irreversibly, as we discussed, this enolate of the ester, okay, plus N isopropyl. Okay, and now the next step can occur where you have methylation, and this attacks here and this attacks here, and let me just draw the methyl iodide properly. So this is CH3I, this is kicked out, and the product that you get is methylated ester. Okay, so this is a classic method of alkylation of esters, and I'm just going to give you a couple of more examples so that we can understand the range of reactions that can occur. So let's say I start with cyclohexanone and add NaNH2 and then allyl bromide, diethyl ether, and the product that I get is this. So basically these are potassium or sodium or Na enolates, and they can be generated by using the corresponding potassium or sodium salts. Okay. Now, so ketones and esters are fairly straightforward to react with. The problem really starts, the complications really start when we start doing alkylation of aldehydes. So we touched upon this in the previous lecture as well, but alkylation of aldehydes using LDA, while in theory can occur. So if you start with this kind of compound, you have NLI, right? This principle, this kind of a reaction can occur and give you the corresponding enolate. The only problem that we face frequently is that the aldol reaction, that is the reaction with itself, dominates, and after you do the workup, you end up getting the aldol product. Okay, so this is, you get a mixture of this aldol product and whatever alkylation or whatever that you need to do. So this is 1, 2, 3, right? So the bond between carbon 3 and carbon 4 is what is possible. So aldol condensation basically competes with alkylation even at minus 78 degrees. So we normally do not use LDA conditions for basically alkylation of aldehydes. Okay. And also keep in mind that if you want to do a cross aldol reaction, you still can't do it at minus 78 degrees because self-condensation is going to compete. So we've already looked at this previously. So one of the strategies is to use specific enol equivalents, right? And these specific enol equivalents can be used with several ways. We'll start with the enamine formation. So we already know that, once you add, let's say you take, this is just an example, but once you take cyclohexanone and you add a secondary amine in the presence of catalytic H plus, we've already looked through the arrow pushing mechanism for the formation of such enamines. So I'm not going to repeat it. But what you can do at this stage is that you react this with Rx, number 1, and number 2 is you do H2O H plus and get the corresponding alkylated product. Okay, so the mechanism of this reaction is something that we have previously looked at, but very briefly, I'm just going to draw out the key step. This is your enamine. Now the key step here is the reaction with Rx. So if you notice that in the previous example and as well as this example, the main mechanism of alkylation or substitution is actually SN2. Okay. So many of these reactions are going to follow all the same rules that we have studied or same patterns that we have looked at with SN2. So the advantage of using these kinds of enamine chemistry to do these kinds of alkylation reaction are that, number one, with the enamines, the reactivity of enamines is quite low when compared to aldehydes or ketones, and so no self condensation, right? So this is advantage number one. And second one is that it's a very mild method. So, it is compatible with or potentially compatible with many functional groups, right? So this is very useful because when we use harsh conditions such as LDA and so on, you can have multiple reactions occurring in a complex molecule. Okay. So some of the other electrophiles that can react with such enamines are, we already looked at alpha bromination of ketones. You can react it with this. It can react with Br and so on. Okay. So I will not go into further details because we already looked at several examples, and also when we looked at aldol condensation, we were also looking at the several examples of this. Okay. So now the next method, which we have already looked at, is to generate ASA enolates. Okay. So the ASA enolates are again a very useful method, and the way we do this is starting with an aldehyde. You react this with R prime in H2, and I'm not going to draw the arrow pushing mechanism, but you will agree that this kind of product can be formed. And now to this, you add a strong base. Okay. For example, you can add a LDA, or you could add butyl lithium or Grignard reagents, and any of these are going to pick up this proton. Okay. And you end up getting the carbanion, which is nothing but ASA enolate. Okay, so as you can imagine, the ASA enolate is more reactive compared to the enamine, and it acts as a much better nucleophile. And when these ASA enolates are reacted with, just draw it out on the next page. So the example that I'm going to look at is I start with this aldehyde and first react it with tertiary butylamine, and we end up getting, right, and then we add a, let's say, MgBr, and the product here, or the intermediate here that is formed, is the ASA enolate. And now you can react this with electrophile such as benzyl chloride, and then you have MgBr, and plus you could also have a covalent bond over here, depending on the nature of that intermediate in solution. So you're going to be able to kick the chloride out. So again, this is like an SN2 reaction. I would urge all of you to go back and look at your basics of SN2 reactions, and so that you can get familiar with it. Okay. Now, when you hydrolyze off this in aqueous acid, you get the product, which is the corresponding aldehyde. Okay. So again, I'm not going to go into the mechanism of this reaction, but this is something that we have looked at. So you start with this, and then you add H2O, H plus, and the product that you get is the aldehyde. Okay. So therefore, in order to do alkylation on aldehydes, the preferred method is to be able to generate the ASA enolate, and then you react it with an electrophile. So we already looked at some examples about how to generate the ASA enolate. Okay. So please go back to your textbook, and this is of course discussed in chapter 23 in Claydon. So please go back and look. There are several examples of this alkylation reactions in the textbook. The next major way to actually go forward to alkylate an aldehyde is the way we have looked at previously, which is generation of the silyl enol ether. Okay, so if you start with an aldehyde such as this and react it with triethylamine, Me3SiCl, the product that you get is the silyl enol ether, and this is actually, this carbon silicon bond is going to, or this carbon oxygen bond, I mean, this is always going to be present at the other side also, just drawing this out in this method. And silyl enol ethers, as you know, are very stable, they can be isolated, and so on. Okay, so the reaction of silyl enol ethers, you may recall, requires a Lewis acid, such as titanium tetrachloride. And from the electrophile standpoint, we typically use electrophiles that require a Lewis acid, for example. So the kind of electrophiles that we look at are hindered electrophiles, statically hindered electrophiles that can, in principle, form carbocations. So let me just qualify my statement. So let's say I start with this tertiary butyl chloride, and when we expose this to TiCl4, what we could expect is the attack of this TiCl4, and you produce this kind of a carbocation with the counter ion as TiCl5 minus. Okay, so this carbocation now is well set to react with the silyl enol ether, and presumably the reaction goes with this kind of a mechanism, and you end up with a product which is going to look like this. And the rest of the mechanism is identical pretty much to what we have studied in the past. Okay, so you end up with a double bond and positive charge, and then chloride ion, which is being produced here, will attack and give you back the aldehyde. So the product that you get is basically C double bond O with the alpha position contains a tertiary butyl group. This is the new tertiary butyl group that is formed, and this is an aldehyde. Okay, so keep in mind that this kind of a silyl enol ether method works very well with the electrophiles that can, in principle, react through an SN1 type mechanism, whereas the previous examples that we looked at are with SN2 type alkylating agents. Now, the last method which we are going to look at is to use beta dicarbonyl compounds. We have already looked at it in the previous discussion. So you start with something like this, diethyl malonate, and you generate the enolate by adding something like sodium methoxide and ethanol. And we already discussed that the ester, since you're doing it in ethanol and sodium methoxide, it's going to react and give you back the ester. So you might recall that. So we are now going to react this with this enolate, OET. Okay, and now let's imagine that we react this with something like chloride over here. Okay, so this can either attack on this carbon or it can attack on this carbon. The product would be the same. You end up with C double bond O ET, C double bond O ET, and this is now bound to a 5-membered ring. Okay, and you may recall that in the previous discussion, I had mentioned that we could sort of convert this bis carbonyl compound or this 1,3-dicarbonyl compound to a monocarbonyl compound. And I'm going to just outline how that can be done. So after you do the alkylation reaction, COOET, let's say we react it with this kind of a ketone, and there is R here. So what you could do is, this is a very old-fashioned technique. It works really well. It gives excellent yields. But what you do is you hydrolyze off the ethyl ester, and you end up with this carboxylic acid. Okay, so here's your main intermediate. And now when you add H plus and you heat, there's a decarboxylation reaction that can occur, which basically cleaves off this carboxylic acid. Okay, and it gives you CO2. Okay, so let's look at very briefly the mechanism. So you have C double bond O, R, just drawing it a little differently so that's easy for us to see this. So this is the hydrogen, this is the oxygen. Okay, so now when you add acid and heat, the kind of mechanism that can occur, or the kind of arrow pushing that occurs, that we propose is the following. This carbon-carbon bond breaks and you get the corresponding enol as the product plus CO2. Okay, which can tautomerase to give you the ketone. Alright, so this is a very, very useful method going forward, because literally, although you're losing a molecule of CO2 in the reaction, it's a very, very selective reaction, so you can actually control the outcome very nicely. And again, this is a reaction that requires SM2 type conditions. So the last example that we look at is this 1,3-dicarbonyl compounds allow you to make cyclic compounds as well, because if you react this with the compounds such as this, okay, so the first step is obviously reaction with NaOET, and then you add in this dibromide, so you can end up with OET. So this is 1, 2, 3, 4, and then you have the bromide, so through the enolate formation, and then the second enolate can be generated, and subsequently you have reaction at the, so this is the second enolate, and this can react with this carbon bromine bond, and you're going to get a 5-membered ring. Okay, so I'll just renumber these carbons. So 1, 2, 3, 4, and that's the 5th carbon. So this is 5, 1, 2, 3, and 4. You can also make a 4-membered ring using this process. And then the interesting thing that you could do is that once you have this kind of a COOET, COOET, in 2 steps, you can, by first doing sodium hydroxide, and then the second step is H plus and heat. You can do a decarboxylation reaction and end up with corresponding carboxylic acid, which can of course be further transformed if you want to. Okay, so to summarize here, there are 3 important methods that we can use. The first one, in addition to direct enolate generation, you can generate the enamine. Alright, the second one is to further generate the ASA enolate. So what we need to do is we need to start with primary amine, for example, you generate the ASA enolate, which is looking like this. Okay, or it could be a covalent bond also. And the next method is to use the trimethyl silyl ether that we are quite familiar with. And the last one is to use a 1,3 dicarbonyl type compound, which can then be easily deprotonated and reacted with. Okay, so this is the one that goes through an SN1 type reaction, because addition of the corresponding titanium tetrachloride or Lewis acid is going to generate the carbocation. So these are the major methods by which one could do alkylation of enolates. The methods are quite similar to the ones that we looked at with aldol reaction.